All right, so the question is, on number 29, sodium hydroxide is added to phosphoric acid. And the question has to do about states. So what are the states? Normally when we see an acid, that's going to be aqueous. And so phosphoric acid, what's the formula for phosphoric acid?
H3PO4.
H3PO4. Right. And this is also a very common acid, phosphoric acid. Sodium hydroxide, normally in pure form, all ionic compounds are solids, liquids, or gases. In pure form, like table salt would be solid, yeah. Ionic compounds are normally solids. If there's water around, then they dissolve if they're soluble. All sodium salts are soluble, so they would dissolve. So if we had phosphoric acid, which were aqueous, then there are two things we could do to this. One, we could add aqueous sodium hydroxide because the sodium hydroxide would have dissolved in the water of the phosphoric acid. Or two, we could have added solid sodium hydroxide. It's not going to stay solid for very long because what would happen is if you added solid sodium hydroxide to phosphoric acid, it will dissolve in the phosphoric acid. So either one is okay. It depends on, at what stage you're doing this. Before the reaction takes place, that sodium hydroxide will dissolve. Normally it's sold in pellets like this. If you have powdered sodium hydroxide, it's hard to work with. Even with pellets of sodium hydroxide, it's hard to work with because sodium hydroxide loves water. And so what it does is it sucks up the water from the air and starts to form, form a pool, a little puddle. And we call it deliquescent. Have you ever heard of the word deliquescent? Deliquescent means it just takes up so much moisture from the air that eventually we just get a puddle of sodium hydroxide if we just leave it out. So either of these is fine. We could take solid chunks of sodium hydroxide and drop them in the phosphoric acid, then that's going to convert it to aqueous. When we do the chemical reaction, we normally will just do it from the aqueous state, so that's okay. It's not clear. It's not clear, but normally to make it clear, they would have said something like this: aqueous solution. If there's an aqueous solution of sodium hydroxide, then that's for sure aqueous. Here it's a little bit ambiguous, so they could be meaning solid sodium hydroxide, like solid table salt is added to water, then it would dissolve, versus a salt water, as is. Okay, were there other questions too?
Yeah, on number 33, they have butane gas reacting with oxygen, and in the answer key, they list butane as a liquid.
Okay, yeah. That is just, if they say butane, butane is what we call very volatile. If you take a look at a butane lighter, a butane lighter, the ones that are refillable will have a little thing where it shows. And so usually we have a little pool of liquid butane, C4H10 liquid. But C4H10 is very volatile. And so what happens is a lot of it will vaporize off the surface. And so this is the same kind of situation where the butane gas is what's going to be igniting. And so, but the common state of butane is liquid. It's just the boiling point of butane is very close to room temperature. So let's take a look at butane here. And normally when we do chemical reactions, we do it based on what's the most stable. state under normal conditions. And so the boiling point is 30.2 degrees Fahrenheit. Oh, 30.2 degrees Fahrenheit means it should be a liquid. And so this must be compressed, you know, in order to liquefy it at room temperature. And so I think this particular problem, it should be a gas. This particular problem, they're thinking in terms of butane lighter, maybe? You know? Or when you buy a tank of butane, because if you buy butane like a cylinder of gas, you're getting a lot of empty space. And so when we buy butane, it would be nice to buy liquid butane because you can get a lot more butane packed in there, because all the butanes are going to be touching one another here. And so it's going to be like 1,000 times more dense in the liquid phase than it is in the gaseous phase. So if you're buying something by the volume, you want to buy it either as a liquid or solid. Because in the gaseous phase, you aren't getting a lot of material. So what did they have? They had liquid. Yeah, it should have been a gas, right? Because under normal conditions, butane's a gas. This would be under higher pressure conditions. It's the same thing with propane. Propane's normally gas, but when you go fill a propane tank, they liquefy it. And so if you pick up a propane tank and shake it, you can hear the liquid propane swishing around in there. And it's just because it's a higher pressure. Higher pressure will liquefy things. But this type of thing, you don't have to really worry too much about liquid or gas. Uh-huh.
For chapter 7,
Mm-hmm.
I'm having a hard time like figuring out the difference between molecular units and formula units. Like when we would
The formula unit you use for everything. Formula unit is valid for any compound or any element out there. So a formula unit for hydrogen would be H2. A formula unit for water would be H2O. A formula unit for salt would be NaCl. So formula units are used for everything. But not everything forms molecules. So for example, would you say, what is the molecular formula of helium? And you go, oh, the molecular formula for helium is He, but helium doesn't form molecules. Molecules are two or more atoms bonded together. Helium just stays alone. And so you wouldn't call this molecular. The only thing you would call molecular are things that actually form molecules. Things that form molecules, the easiest way to remember what forms molecules, the compounds that are formed from nonmetals. Compounds that are formed from nonmetals will be molecular. So, for example, butane, here, carbon's a nonmetal, hydrogen's a nonmetal, is a compound, and so we call it a molecular formula, or a formula unit, either way. Water, you know, oxygen's nonmetal, hydrogen's a nonmetal. Our barium oxide, barium's a metal, oxygen's a nonmetal, and so this is not a molecular unit. What we call this is a formula unit, and so when we talk about the formula for this, we would never call this the molecular formula. We would just call this the formula unit or the empirical unit for this. It's just the simplest unit there. And so there are exceptions, you know, something like ammonium nitrate. Ammonium nitrate consists of all nonmetals, but it's not molecular. Ammonium nitrate's ionic because it consists of the ammonium ion and the nitrate ion. Just like ammonium perchlorate. Do you recall or remember ammonium perchlorate was used for what?
The pepcon.
The pepcon. And pepcon, they manufactured rocket fuel. rocket fuel ammonium perchlorate. So there are some groups that are trying to make a greener rocket fuel for use. In fact, there was a pretty interesting article that popped into CME News. Maybe you can find that in the letters section. Of lettuce and rocket fuel, is this the one? Oh, greener rockets. Maybe this is it. Studies released last week finding perchlorate in lettuce have focused attention on a struggle between EPA and the Pentagon over cleanup standards for the chemical perchlorate, a component of solid rocket fuel. Disrupts thyroid uptake of iodine and taints water supply in 20 states. I know Riverside's been working hard at getting rid of the perchlorate. Riverside, the municipal water district, I think they have these giant filters that are like reverse osmosis to clean it out, etc. So they're looking at other alternatives for this. I'll show some other stuff. Well, speaking of iodine uptake, so if there's ever, I know there's some, like, I read that the government just spent a bunch of money on radiation drugs, the radiation drugs for the platelets, but, that's gonna be hard to get your hands on, but if there's ever some kind of radioactive, hopefully there won't be, because, when I was going through elementary school, I don't know if they have these, this is back in the old days, we'd have nuclear bomb drills. You know how the nuclear bomb drill? Go under the desk. Come on. So then I'd always worry, like I'd sit in the backyard and I'd look up at the night sky and look, is that a missile coming, an ICBM coming at us from, and so I constantly worried about that, like obsessed about that. And so, and I was always worried about, because they always portrayed, Russia as some evil, and Russia and China as evil, and the people are evil, and this and that. And then when things calmed down, then I finally could relax, But now I'm starting to get that weird, unfortunately. But anyway, iodine is something you want maybe to get. Not iodine, but iodide. Iodide goes into your thyroid. And so iodide uptake. But, a lot of people aren't chemists, and if you say iodide, then, they might not know what you're talking about. So iodine, everybody knows that's an essential element for your thyroid function. And so maybe these iodide things, that I showed the other day might sell out like they did after Fukushima. Who knows? All right, does that answer the question? You just look. These are going to be exceptions, but anything else that consists of all nonmetals and it's a compound, you call molecular.
Okay.
Basically.
And formula units are?
These are all formula units. Everything's a formula unit.
Yeah, but like what I'm trying to understand is when you're doing dimensional analysis on, like for instance, you're trying to find how many molecules are in iodine, for instance, or iodine.
Mm-hmm.
So that's where I'm struggling, is trying to figure out, okay.
Yeah, that becomes tricky.
Molecules or formula units?
People, sometimes, like when we're doing empirical formulas, I see this all the time. You know, so let's say we're analyzing the compound CXH10. And let's say they had CXHY. Let's say they had blank, blank, blank grams of carbon. Okay, that's okay because we can convert that to moles of carbon quite easily. It's, 12.01 grams of carbon per mole of carbon. And so we can get the moles of carbon from there. But then they go grams of hydrogen, and then people get all messed up here because they think, okay, is that hydrogen atoms or is that hydrogen molecules? So many people do this. They'll say 1 mole of hydrogen molecules, H2, is 2.016 grams of hydrogen. And then they end up with moles of hydrogen molecule. But does this contain hydrogen gas? Butane contains a mixture of hydrogen gas and, let's say, graphite or diamond. No, it's yeah. So when we're doing this, you just figure we do dimensional analysis with lots of different things. Sometimes we're doing it with atoms. Sometimes we're doing it with molecules. Sometimes we're doing it with formula units. And if we want to know how many molecules there are, then we can do that. If we know how many moles, if I had 1 mole of butane, I can say, well, 1 mole of butane is going to contain an Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd butane molecules. So we say molecules here per mole of molecules. A lot of people don't spell this out. They'll just say this many per mole. Yeah. And that will give you how many molecules. If we have 1 mole of sodium chloride, we wouldn't say molecules of sodium chloride because this is a metal and a nonmetal. Metal and nonmetals don't form molecules. So what we'd say instead is there's 6.022 times 10 to the 23rd NaCl formula units. Now what a formula unit is, and I just abbreviate it like that, is 1 sodium atom and 1 chlorine atom, or 1 sodium ion and 1 chloride anion. Formula units, and that will just tell me I got that many formula units. I could do the same thing. I could call this formula units too, but I can't call this molecules because it's an ionic compound. Is that?
Yeah, that makes sense, but for the diatomic ones, like
Iodine?
yeah, I2 or N2.
If we have 1 mole of iodine, first we have to ask, is that atomic iodine? Because what people do is they buy or is that atomic iodine or iodide maybe? So what I was looking for are iodide tablets. Iodide tablets, nuclear war, or something like that, let's say. Take potassium iodide pills before or immediately after the interaction with radiation ensures that the gland is saturated with the iodine. And since there's a lot of perchlorates in the Colorado River from Nevada, maybe your iodine uptake isn't as high as you have perchlorate in there. Iodine, now this is iodine versus this. So when they're talking about iodine here, they're actually talking about atomic I. So how much iodine is in, or how many atoms of iodine are we going to get? And so sometimes it's sloppy. Sometimes you don't know because usually when we think about iodine, we think about I2. Right? Mm-hmm. And then actually that's what I did in my nose and my throat gargle with I2, iodine or iodine. Iodine. But here, for this, we don't want to take iodine, we want to take iodide, but most of the public doesn't know the difference between iodine and iodide. so that's why it's all mixed up here. Iodine tablets should be taken less than 24 hours before exposure and no more than 2 hours after contact. Well, that's according to this website. It doesn't, yeah, they don't stop radiation. Why people are buying potassium iodide pills. This is from the Nuclear Regulatory Commission. I'm kind of curious what the NRC says about potassium iodide. So this is a government agency. What is potassium iodide? Potassium iodide is a salt similar to table salt. Its chemical symbol is Ki. It is routinely added to table salt to make it iodized. Potassium iodide, if taken in time and at the appropriate dosage, blocks the thyroid gland's uptake of radioactive iodine and thus could reduce the risk of thyroid cancers and other diseases that might otherwise be caused by exposure to radioactive iodine that could be dispersed in a severe nuclear accident. What is the role of potassium iodide in radiological emergency preparedness? Potassium iodide is a special kind of protective measure in that it offers very specialized protection. Yeah, it's very specialized. It's not going to protect you from anything else. You know, when I looked at what the government was stockpiling, I think they just bought $250 million worth of drugs for radiation sickness. That's totally different. That one you're not going to be able to get. An over-the-counter purchase. But potassium iodide you can get, that's easy to get. This people use it as salt. Is there a question? Or you know, if you live near a nuclear reactor, then you probably want to have some. The purpose of radiological emergency preparedness, although you know San Onofre is offline. You know that? San Onofre nuclear power plant. I had a friend who just got a job at San Onofre nuclear power plant as a safety officer there, and then right after he got the job, he had quit his other job, which was a really good job. They closed the plant down. They had problems with the nuclear fuel rods. The metal that they purchased a whole bunch of nuclear fuel rods, and the metal was, I think, very brittle, and so it was breaking. But there's a whole bunch of spent or nuclear waste stored at San Onofre. There are tons and tons of nuclear waste stored at San Onofre that people are a little bit concerned about. I think, you know, those generation of nuclear power plants are the older generations. And so the newer generation of nuclear power plants are much safer. I think, and they're looking at doing smaller ones rather than these big ones, but they take many, many years. You know, the permitting process is so long that, you know, the technology becomes less and less current. So, maybe. I'm not totally against nuclear power. But when people start talking about, you know, I think I told you that the government in Japan, they want to dump the nuclear waste into the ocean. Did I tell you that? Yeah, that was just though I was thinking, if they're going to do that, then why don't you just take the San Onofre nuclear waste and dump it into the ocean? You know, this is the same thing, isn't it? Just unbelievable, I think. But anyway. So here, you might think about getting some of this potassium iodide. You know.
So going back to the formula units and the atoms, say you have This one was, what is the mass of 4.12 times 10 to the 24 nitrogen molecules? That's where I know nitrogen should be atoms.
No,
or-
they said nitrogen molecules. If they say nitrogen molecules, then you already know it's N2. So they're making it very clear.
Okay.
When we say iodine, it gets all mixed up. Are they talking about I or are they talking about I2? You know, it's ambiguous. So if you say iodine or iodide, you know, it makes a difference. Here, you know, the problem is something like this. We say hydrogen. Normally when we think about hydrogen, you know, how much hydrogen is in butane? Normally when we think about hydrogen, we're thinking H2, but that's wrong. In this case, we're thinking about H, how much H is in. And so it depends on the context of the question. And so in that particular question, they're trying to make it clear that they're talking about N2 rather than N
Okay.
by saying molecular. Now, if they just said nitrogen, then we don't know. If they just said nitrogen, you don't know. Just like this. If they said, okay, you should take iodine in the event of a radiation disaster, you know, okay, you should take iodine. You could be taking iodine, not iodide. You know, it's ambiguous in that case. You know. Although, you know, after Fukushima, most of the places were sold out of potassium iodide, and so people were buying iodine as an alternate to that. It is kind of harsh, you know, to that. This is for those people who worry about those stuff.
So nitrogen when it's 1N, it's atoms, and nitrogen when it's N2 is molecules.
Yes.
Okay.
Yeah. When nitrogen is in ammonium nitrate, that's atoms. Even though we have two nitrogens here, it's not N2. You know, even this always gets people. If I had magnesium chloride, a lot of people will tell me that's chlorine, Cl2, in magnesium chloride. No, it's two chloride ions in a magnesium. It's not chlorine gas, which is a green gas, mixed in with this solid. You know? And so whenever we have a compound like this, it's always going to be by the atom. So even though there's oxygen here, it's not O2, it's O. Same thing here. Does that make sense? And so we have to think about that. It's not always clear though. It's just the same thing. It's like the state. You know, if somebody said sodium chloride, you don't know. Are they talking about aqueous or are they talking about solid? Sometimes you just don't know. So you pick one, sodium hydroxide. You know, if they're going to be ambiguous, then you can be at liberty to assume one or the other. Or you could do both. Okay. This is clear though. Chlorine gas. If it's chlorine gas, that's got to be It's got to be Cl2. Zinc metal. That's got to be. It's got to be zinc solid, liquid, or gas, or aqueous. Solid. And, you know, when you think about a piece of metal, all metals are solid except for one. Which metal is a liquid? Mercury. That's it. Every other metal is a solid. But sometimes they won't say metal. Sometimes they'll just say zinc is placed. You still know that's zinc metal because there's no charge. Zinc is fixed charge. And therefore, if they meant ion, they would have had the right ion here. So we know that that's zinc, just zinc, zero charge, metal, solid, not Zn2+. Is that clear? If this said zinc ion is placed in, then we know it's Zn2+, because zinc only has one ion. It's the 2+ ion. Here's chlorine and potassium reacting very violently. You know, chlorine's what we call a strong oxidizer, and potassium is electron rich, and so we get a nice redox reaction there. It's quite violent. This is more violent than throwing potassium in water, because water is not a very good oxidizer. Chlorine's a much more powerful oxidizer. I mean, people drink water, like this water there, but people don't drink or inhale chlorine, because it's much more reactive. And so potassium and water react very violently, therefore potassium and chlorine would react even more violently. The only difference there is this. Chlorine's a gas. Gases, there's a lot of empty space, so it might not be as violent. If it were liquid chlorine, it would be much, much more violent. Water is a liquid, so it's much more dense, so you're gonna get more reaction even though it's less violent. Does that make sense? This is ammonium sulfide. This might be confused here. Is that a molecular or is that ionic? This would be ionic because we would recognize ammonium ions and sulfide ions. And you go, okay, that's ionic. You know, otherwise, if it's all nonmetals, you assume it's molecular, unless you can recognize the ions here. Phosphorus tribromide is produced when phosphorus reacts with bromine. Now, what bromine do I use here? Br2 or Br? Br? Okay, in this case it would be, you know, phosphorus reacts with bromine. It's going to be Br. Well, we think, what is the most stable form of bromine? It's going to be Br2. But when we form phosphorus tribromide, then there are no Br2s in here. These are bromides that we have. Yeah, 3 of them. This is, you know, there's exchange of electrons is happening here in that sense. Silver nitrate is added to a solution of sodium sulfide. Now, silver nitrate, that's ambiguous. That could be aqueous or solid. Either way, it's fine. But not all nitrate's also soluble. So when it's added to the solution, everything's going to be dissolved in water. In this particular case. Is this chapter 8? What number did you make it to?
For chapter 8?
Yeah.
I did all of the homework.
All of the homework for chapter?
All the assigned ones.
Okay. Well, I need to talk about a couple of things from chapter 8. So you got the pattern down, but there was one that didn't quite fit the pattern. That was chlorine with potassium iodide, number 21 here. So I want to talk about this one a little bit more. I told you for this one to, what did I tell you to do for this one, number 21? I think I told you to memorize a second pattern, is that right? The pattern with the halogens. But we don't have to memorize the second pattern because there are other exceptions to the single replacement. There's an alternative to single replacement pattern. The reason we need this alternative is because the single replacement pattern fails. Like, for example, in 21, the single replacement pattern was A plus BX yields AX plus B. And so it failed. It fails sometimes. what happens is we have an element here, and this element gets converted into a cation here, A plus X here. Cation is just a positive ion. And then we have a cation here, B plus Y, let's say, and that gets converted into the element here, element B. And so that means A loses electrons, and B plus Y gains electrons. If something gains or takes electrons, we call that the oxidizer. And so B plus Y is the oxidizer. So oxidizers take electrons. And A is what we call the reducer. The reducer loses electrons. So not everything fits this pattern, and so that's a problem. The problem is not everything fits this pattern. So if I think about chlorine plus potassium iodide, this should form, well, let's first look at it here. This should form, it should form chlorine iodide, monochlorine monoiodide plus, actually, potassium metal. Chlorine's a gas. These are going to be aqueous. This is aqueous here. This turns out to be wrong. The reason it's wrong is this. You know, do people eat potassium iodide? Yeah, if you buy iodized salt, there's potassium iodide in there. Or sea salt, I'm sure has potassium iodide in there. So people eat this stuff, right? And so in this case, we have potassium ions. This would be the oxidizer. And then chlorine, this should be the reducer. But there's something funny about this, and that is, what is more reactive? Potassium ions or chlorine gas? Chlorine gas. Chlorine gas is much more reactive. And so the roles have been misassigned. And so let's say you're a movie director and you have some actors, and you totally botch the assignment of the actor. So you say, okay, potassium ions, you'll be the oxidizer. And then chlorine, you're going to be the reducer. But the problem there is that chlorine's not a reducer. Chlorine is a powerful oxidizer. And so the roles have been misassigned. And so the play or movie or whatever you're the director of is not going to quite go as planned, probably, because you know, in nature they're just going to let whoever reacts, you know. And so in nature, what do you think is going to happen? Do you think chlorine is going to patiently wait and not take anybody's electrons, or chlorine's just going to go ahead and attack? What, you know, maybe there's a police, you know, a molecular police or atomic police that come in and say, don't take electrons. Do you think that there's something like that? There's nothing like that. The chlorine's going to take electrons, right? Chlorine's going to want to take electrons. And so what's going to happen is their natural, you know, roles are just going to be realized. I mean, if chlorine's an oxidizer, it's going to be an oxidizer no matter what you call it. You can try to call it a reducer. You're going to be a reducer. You're going to be a reducer, but its true nature is going to come out. And so this is wrong. Potassium ions are the worst, one of the worst oxidizers there are. Potassium likes to lose electrons, potassium metal. Potassium metal likes to lose electrons to form potassium ions. Potassium ions are stable. You know, some people like the way they taste. Just like sodium ions. So this is wrong. And so the alternative to this is called the chart method, and the chart method is just to let everybody, you know, adopt their preferred properties. All right, so there's some steps in the chart method. One, we do something called an inventory. That is, we figure out everything that's present. So what's present? Well, what's present is we have chlorine, we have potassium ions, we have iodide ions, and we have one more thing. Do you know what one more thing is that's present? There's a lot of it. There's one more thing present here.
Water, it's aqueous.
Yeah, it's water. It's aqueous. This is not solid potassium iodide. So it's aqueous means there's lots of water to dissolve that potassium iodide. So we have to factor that in. And then we look for what they like to do. Sometimes it's not so easy, like sometimes we need a little bit more analysis. But since you're just learning, we're not going to analyze these. We're just going to look them up on a chart, what they like to do. Unfortunately, the chart is all the way out in chapter 19, section 19.5. Page 567. So, for example, what does fluorine like to do? Does fluorine like to take electrons or lose electrons?
Take electrons.
Fluorine likes to take electrons. And if you look at the ranking here, it's ranked from stronger down to weaker. So that means fluorine must be the strongest what? Yeah, and in fact, fluorine's the strongest oxidizer on this chart. Sorry. Fluorine's the strongest oxidizer on the chart. It really wants the electrons to form fluoride. So you could brush your teeth with fluoride because fluoride's fairly stable in the sense that, you know, once it has an electron, it's happy. But you wouldn't want to brush your teeth with fluorine. That would cause tremendous damage. Some gold, there's gold 1, gold 3. Gold 1 and gold 3 are unstable because they're powerful oxidizers like fluorine. And then here's chlorine. Look, there's fluorine. Chlorine's a little less powerful. Here's oxygen. This is oxygen in what we call acid. Acid is H+, so oxygen and acid. Here's bromine liquid. So it goes fluorine, chlorine, bromine, and then iodine's down here. The iodine's not nearly as powerful as these. Iodine's normally a solid, but you can mix it with water to form an iodine solution. But iodine wants electrons. And once it gets those electrons, it forms iodide. Iodide's happy, but iodide, you know, is not as happy as fluoride. Fluoride is good. Fluoride's very small. When we look at iodide, iodine's quite a bit bigger. So if something more powerful, iodine's a good oxidizer, but if something more powerful comes along, it can take the electrons from iodide, you know, being big. So we have a name for that. So if iodide loses electrons, that's called a reducer. And so this chart is pretty interesting because it shows the oxidizers on the left, and this one shows the reducers on the right. If fluorine's the most powerful oxidizer, then fluoride has got to be the weakest reducer because fluoride does not want to lose electrons. So fluoride is going to be the weakest here. Do you know what the strongest reducer is? The strongest reducer is at the bottom here, and that's lithium metal. Lithium metal easily loses electrons to form lithium ion. And so lithium does not hold on to the electrons. That means lithium ion is not a very good oxidizer. Lithium ion doesn't really take electrons. You know, it's happy as lithium ion. Same thing with potassium. Potassium metal is a very powerful reducer. When it loses electron, it forms potassium ions. Potassium ions are stable. They're unreactive, just like sodium ions. You know, sodium ions we don't think of as a strong oxidizer. And so these are very weak oxidizers here, like sodium ion. So if you're trying to kill viruses or bacteria, sodium chloride is not going to work. You know, sodium ions are stable, chloride ions are stable. They're going to be unreactive. Maybe you could dry them out. You know, that might work. Or too much sodium chloride might work, but it doesn't work like that. And so all we do is we consult the chart. So what we do is we look for chlorine up here. Is chlorine on the oxidizer side, or is chlorine on the reducer side? And chlorine and chloride are two different things. So when I look at chlorine, that's Cl2. Cl2 is on the oxidizer side. And so it's an oxidizer. So when we inventory this, we have an oxidizer here. And so what we say is, I call this an OA. OA stands for oxidizing agent. OA. Then I go to potassium ions. If I look at potassium ions here, is that on the oxidizer side or the reducer side? Oxidizer. So potassium ions are an OA. Now let's say there's a competition for electrons. Who will win? Chlorine or potassium ions? Chlorine. Chlorine will win. When I look at the single replacement says no, chlorine doesn't win. In fact, chlorine's going to be a loser. It's going to be potassium ions that win. But does that make any sense looking at this chart? It makes no sense at all, as potassium ions are very weak. Then we go to iodide. We look at iodide and we try to figure out what side is iodide on. It's over here. That's on the reducer side. And so iodide is a reducer. And we call this the RA. RA stands for reducing agent. This chart is not comprehensive enough for us. Oh, maybe it is. Because there's one more thing here, and that is water. Now, water is very interesting because when we look for water, do you see water here? That's on the reducer side. So we'll just say water is an RA, but water is quite interesting because it's also on the oxidizing side. It's not shown here, but it's shown on this chart up here. So what you need to know is fluorine. What do you know about fluorine? Tell me one chemical property of fluorine, F2. It's the strongest oxidizer on the chart. So when we look at this, I don't see fluorine up here, you know, on the top left. What do I see? Lithium metal. But then I found fluorine down here on the bottom right, which tells me this table relative to that table is inverted, it's upside down. And so fluorine here on the bottom right is the most powerful It's oxidizer, and lithium at the top left is the most powerful reducer. And so, it turns out that water occurs on both sides of the chart. So if I start off at fluorine and go weaker, weaker, here's bromine, there's chlorine, bromine, up here's iodine, it's weaker and weaker, weaker and weaker, and then eventually I hit water. You see water here? Water is between aluminum 3+, so water is a better oxidizer than aluminum ions, but a weaker oxidizer than zinc ions. And so water is in between zinc ions and aluminum ions. And so that places water right here. As far as rank goes, water is here, between aluminum and zinc. And so water belongs here on the left side of the chart, but they didn't put it on this chart. So we have to insert that in here. And that means water is very interesting because it goes either way. Water can either be a reducing agent or it can be an oxidizing agent. And so it could act as either. And so we inventory this. Then what we do next is we find the strongest. And so two, react the strongest OA present with the strongest RA present. So what we have to do is we have to figure out which one of these is the strongest oxidizer. We have three choices. We have chlorine, gas, potassium ions, or water. Which one do you think is going to be the strongest? Yeah, chlorine. We probably don't even have to look at the chart because of our experience with these. We have two reducers. What are the two reducers? Iodide or water? So which one loses electrons more easily? What would your guess be? Well, we don't have to guess. We could just look at the chart. Iodide or water, which one loses electrons more easily? Well, what loses electrons the easiest? What loses electrons easiest would be lithium metal. So we'll just keep going up. We'll get weaker and weaker. And which one will we hit first? We're going to hit iodide first before water. And so iodide is a stronger reducer than water. And so the strongest oxidizer is going to be chlorine, the strongest reducer is going to be iodide. So if there's any reaction here, it's going to be between the two strongest species. Okay, then what we do is we copy down. So when chlorine reacts, what does it do? It takes 2 electrons to form 2 chlorides. And so we copy this down. When chlorine reacts, it takes 2 electrons to form 2 chlorides. Now, we read this, we only go on one table for both, so we have to read these backwards sometimes. So when iodide reacts, so what we want is we don't want iodide a product. Right now this is called a product because it's on the right side. What we need to do is we need to put iodide on the left side and make it a reactant. And so what I do is I'll put iodide on the left side, and so I have to flip the equation because I want this to be a reactant. Chlorine's a reactant, iodide's a reactant, and so both of these are reactants. Okay, so what happens is, if this is reactant, then it's going to go to these products here. So we're going to flip this equation over. So that's going to be 2 iodides. 2 iodides will go to iodine plus 2 electrons. Okay, when we react these, we'll add up these 2 equations. And so add up the equations, making sure that the electrons have to cancel out. So if this one gains 2 electrons and this one loses as a product, then they have to cancel. And so combine, these are called half reactions. Combine the half reactions making sure electrons cancel. They don't really cancel. I mean, they're still there. Electrons are cancel in parentheses. The electrons balance. In other words, they have to balance. And when we add up the two half reactions, we get what's called the net reaction. That is, chlorine gas will attack two iodides and take the electrons. Who wants the electrons more? Chlorine wants the electrons more. Chlorine's more powerful. And that means iodine's going to lose. So iodine loses those electrons to form I2, and chlorine gains those to form chlorides. So this is just a tug of war. Who's stronger in the tug of war? Chlorine is. You see that? 3, determine driving force. Well, DF. DF is called driving force. So what we have to do when we determine the driving force is we have to look at, yes, this is the most likely reaction to occur, but is it going to occur? And the driving force is stronger, OA, RA, to weaker, OA, RA. So stronger oxidizers and strong reducers are very reactive. They're unstable. Weak oxidizers and weak reducers are stable. They're very unreactive. So what we want to do is we want to go from something that's unstable to something that's stable. And the way we determine that is by assigning these. So chlorine and two iodides. The role of chlorine is as the OA, and iodide is the RA here. This is going to go to iodine plus 2 chlorides. Now what we have to do is we have to imagine this reaction occurring backwards. If we imagine this reaction occurring backwards, what happens to chloride going backwards? If we go backwards, chloride loses electrons, and anything that loses electrons is called a reducer or oxidizer. Reducer. So if we were to go backwards here, then this would be an RA going backwards. If we were to go backwards here, then iodine takes electrons, meaning it's the oxidizer. So this would be the OA going backwards.
How do we know when a equation can go backwards?
Well, we do this when we figure out the driving force. The driving force is either it's going to, the driving force is we're trying to figure out which way is the downhill direction. You know, we can't just look at the reaction and go which side is downhill. Downhill is going to more stable. You know, so if you roll down, let's say you're on the top of a steep hill, then we know we're going to go downhill. But what if you're at the bottom of the hill? And so if we're at the bottom of the hill, then we might go uphill. Is going uphill favorable? No, it's unfavorable. You don't want to go uphill. You want to go downhill. So what we're trying to do is we're trying to figure out what the downhill direction is, and we can't do that until we know this. So we do this for everything. For everything, we look at reversing it and then seeing which way is downhill, which way is uphill. And so when we do this, we'll see that iodine is going to be the oxidizer going reverse, and chloride is going to be the reducer going reverse. And then we compare the strengths on the chart. You already know this because I've repeated this, I think, a bunch of times. Which one is a stronger oxidizer, chlorine or iodine? Chlorine is a stronger oxidizer. Iodine is a weaker. I said it a bunch of times, but if you didn't know, then you just look at the chart. Fluorine's the strongest, and then here's chlorine, and then iodine's way down here. So that means chlorine is stronger than iodine. Okay, as far as reducers go, I didn't say this, so iodide should be stronger than chloride. If I got this correct, it has to be that iodide is stronger. We call this a conjugate relationship. It's a conjugate relationship because if you have a powerful oxidizer, it takes electrons violently. If it takes electrons violently, it doesn't let them go. And so that means that we have something called a conjugate relationship. That is, if one side's strong, the other side's got to be weak. And if one side's weak, the other side's got to be strong. And that's the conjugate relationship. And so, based on the conjugate relationship, it's got to hold that iodine is a more powerful reducer than chloride. And it is. Lithium's way down here at the bottom. And so what we say here is that this is stronger, this is weaker. And so if this is stronger, that means it's more reactive, less stable. That means this is the uphill side, this is the downhill side. And so this is going downhill. This is a driving force. If this were going uphill, this is stronger. It doesn't have to be strong, it's just stronger to weaker. That's a driving force. If we're going from weaker to stronger, that's not good because that means we have to go uphill. And if that's the case, then we don't expect reaction. There's no driving force. Right, the driving force is just the natural direction it's going to flow. Does water flow uphill? Water doesn't flow uphill. Water flows downhill. This is the same thing with these reactions. These reactions are going to go downhill. Sometimes they go uphill, but we'll talk about that later. There's other things that might influence it. Okay, so we have a driving force here. So the reaction is chlorine is going to assume the role of the oxidizer, not the role of the reducer. And so that was the problem with the single replacement. The origin of the problems with the single replacement reaction are due to misassigning roles. Who's the oxidizer, who's the reducer? The advantage of the chart method is we don't misassign the roles. You know, we just look at everybody individually rather than trying to fit them into some kind of pattern. And so what that means is that there are exceptions. You know, there's a pattern. So let's look at the next example would be copper metal. What's copper metal? It's Cu solid. This is not copper ion. Copper metal is mixed with nitric acid. What's nitric acid? HNO3. That's correct. Now, normally when we do single replacement, we look for a driving force for single replacement. And the driving force for single replacement is something called the activity series here. The reason why the chart is written upside down there is because the activity series is based on reducing strength. All we need is one of these to hold. If one of these holds, then it's true, because it's always got to be strong, strong, weak, weak, or weak, weak, strong, strong. It can never be strong, weak, strong, weak. That will never happen. It's going to be all on one side stronger, all on the other side weaker. And so all we need to look at is one of these. In single replacement, they just like to look at the reducing agent. And if we rank it, then we flip the chart upside down, and we rank lithium at the top, because lithium is the strongest reducer. And so lithium is called the most active element because it loses its electrons really, really easily. And so lithium is very active. In fact, it's so reactive. Water isn't a very powerful oxidizer. No, water is a very weak oxidizer. If we look at water's strength as an oxidizer is here. Water is between zinc ion and aluminum. Well, zinc ion and aluminum aren't that powerful. You know, a lot of people take zinc supplements. Zinc supplements aren't the metal. You know, zinc supplements are the zinc ion with vitamin C. You know, zinc with vitamin C. Right? Lots of people take that, including I've taken it a bunch of times as well. When people were really worried about COVID, they said, take zinc with vitamin C, along with a whole bunch of other things. If you're interested, there's on MedCram, the UCR medical professor, Dr. Schwell, he has a whole bunch of recommendations on supplements to take if you're interested in those. One of those was NAC, N-acetylcysteine, but it was banned, and then now it's okay, I think, to take. So there's some ridiculous ban that happened like last year or the year before. But I just read a study, I didn't know this, but N-acetylcysteine they're studying it for longevity too. And apparently the results are promising as a longevity supplement that is something to learn in your life. You might look at that as well. So going back to this, all these are so powerful that you don't need a very strong oxidizer. These reducers are so powerful, you're going to use an extremely weak oxidizer. What's an extremely weak oxidizer? Well, one extremely weak oxidizer is water. Water, we don't think of water as being a very good oxidizer or a very good reducer, we drink water all the time. And it's very unreactive in that sense. But if you mix it with these metals, like potassium metal and water is very dangerous. Sodium metal and water, very dangerous, because these are very powerful reducers. Very powerful reducers will work with exceptionally weak oxidizers. These ones are less powerful, like magnesium, aluminum, manganese, zinc, chromium, but they're still pretty decent. But if you drop magnesium in water, you don't have to worry about an explosion. Like if you drop sodium in water, you have to worry about an explosion. Magnesium in water, not so much. However, if it's hot water or steam, then you gotta worry. Or acid. Acid is a better oxidizer. Acid, this is a generic acid here. Generic acid is H+. H+ can take electrons, 2 electrons, to form H2 gas. So if H+ acts as an oxidizer, it's going to form hydrogen gas. And so that's one of the reactions we looked at, I think, earlier. But it goes down the list. Gold is one of the worst reducers. And gold is very stable. It doesn't want to react. And so this is the conjugate relationship. Gold doesn't want to react. It's very stable. So if you get it to react to form gold 1 or gold 3, these are going to be extremely powerful oxidizers because they want to revert back to gold. So they'll take electrons. So, well anyway, let's follow this one because this one looks like the A plus BX pattern. So if it's the A plus BX pattern, what do we form? AX plus B. So the thing is, now copper is variable charge. Do you recall what the charge on copper is? +1, +2. That's very good. You can recall that. So what should I form? Should I form copper +1 or should I go all the way to copper +2? What's your advice to me? Go all the way to +2. That's what we're going to be just doing. We'll just take it to copper. If we go to copper 2, that's Cu with a 2+, and what's the nitrate? Its charge is NO3 minus, so we're going to need how many nitrates? So that would be copper 2 nitrate. And B is going to be the element hydrogen. What's the element hydrogen's formula? H2. That's a gas. Nitric acid acids are, at least the acids you're going to be working with are going to be aqueous for now. All nitrate salts are aqueous. In balances, we'll need 2 HNO3s and then it's balanced. Now, are we going uphill or are we going downhill? Okay, so this is what we need to determine. Are we going uphill or are we going downhill? And so in single replacement, we use the activity series to determine that. And the activity series compares the two elements. The more active an element is, the more stable it is, or the more unstable it is. The more active the element, the more unstable. And so the most active element is, the least active element is gold. So if we're comparing the two elements, copper versus hydrogen, we have to think which one is more stable, which one is less stable. And so one thing you could do is you could say, okay, what if you filled the trunk of a car? Would you rather fill the trunk of the car with copper, or would you rather fill the trunk of the car with hydrogen gas? Copper, because copper is a lot more stable, and you don't want like a Hindenburg-style incident in your car. And so what we already know that this is going uphill. How do I know it's going uphill? Because we're going from something more stable to something less stable. So if this is uphill, then I say that's not going to happen, right? And in the jargon of activity, we say we're going from a less active copper to a more active hydrogen. That's uphill, and so there's no driving force. What we want to do is we want to go from more active to less active. If we go from more active to less active, that's downhill. And that would be what we call a driving force. But in this case, we're going uphill, and therefore what we expect is we expect NR. Do you know what NR stands for? NR stands for no reaction.
So you can determine the driving force just by comparing the stability of the two elements.
Yeah. Because they're both reducers. The elements are both reducers, so we're comparing one reducer to another reducer. We could also do it based on the oxidizer, but the oxidizer is a bit more tricky here. And so we do it based on the reducer. The oxidizer would say the same thing. The oxidizer over here is H+. Do you know what the oxidizer over here is? Nitrate doesn't change, so it's Cu2+. And so we could have compared the oxidizers. Cu2+ is a stronger oxidizer than H+. And so what we're doing is we're going from a weaker oxidizer, H+, to a stronger oxidizer, Cu2+. So it's uphill again. But for single replacement, they don't want to make it so complicated. They want to make it simple. And so simple, we just compare the two elements and then see, do we have a driving force or not? Does that make sense? Unfortunately, this is wrong here. The correction would be no single replacement reaction. But it turns out there is a reaction. There is a reaction. use the chart method to try to determine reaction between copper and HNO3. So we determined that copper was on the lithium side and H plus is on the, so look for H plus. You have to be careful because here I see an H plus, but is this H plus okay? No, because we're missing, do you recognize this ion? MnO4 minus, what's that called? Permanganate or manganate? Permanganate, yeah. I see H plus here, but there's O2, oxygen. I see H plus here, but there's NO3 minus. NO3 minus is called nitrate. I see H plus here. Do you see it here? And that's on the, and therefore we call it a oxidizer. And so what's next? Nitrate. So try to find nitrate. Since there are times that water reacts very violently or explosively, we got to worry about it. And so we factor it in here. All right, what's the next step here? We look for the strongest. So tell me which is the strongest reducer and which is the strongest oxidizer. And you can consult the chart to determine. It turns out that nitrate is a very powerful oxidizer. You look at the ranking of nitrate, it's up there. Whereas if you look at H plus, it's significantly weaker here. And so the nitrate, powerful, most powerful. Okay, then what we do next is we just combine. So, actually, combine it. So we take a look at what happens with copper. Now, copper is a reactant. All these are reactants here. But when I look at this chart, is copper a reactant or a product? It's a product. So what I have to do is I have to flip it. And so if I flip it, I make copper the reactant. Then copper solid goes to what? Yeah, copper 2 ions plus 2 electrons. Okay, the next thing I want to do is I want to make nitrate a reactant. Well, nitrate's already a reactant here. And so all I do is I just copy this one as is. Nitrate plus, plus 4 hydrogen ions plus 3 electrons yields NO. What do we call NO? Nitrogen monoxide and 2H2O. Nitric oxide. Okay, these are called half reactions, and what we have to do is we have to combine the half reactions. But when I look at this, this is different than the last. What's different about this combination? The electrons don't balance. How can I make them balance? Yeah, well, to make them balance, we'll just cross multiply. So the first one will multiply by 3, the second one will multiply by 2. So if I multiply this one by 3, that gives me 3 coppers, 3 copper ions, and 6 electrons. if I multiply the second one by 2, that gives me 2 nitrates, 8 H plus, 6 electrons, 2 NO, and 4 H2O. Okay, now I can combine them because what I need to happen is I need the electrons to balance. And so I have 6 electrons on the right side and 6 electrons on the left side, and we can cancel those out. And then we'll just add everything up. And so if I add everything up on the left, I'm gonna do 3 Cu solid. Okay, that takes care of this. Then I add these on the left here, plus 2 NO3 minus plus 8 H plus yields 3 Cu2 plus, so combine everything on the right, plus 2 NO gas plus 4 H2O liquid. And then I compare, what we said was that the copper is a reducing agent, so that's our Ra. And then the nitrate with the H plus, this is our oxidizing agent. So this is our reducing agent. Nitrate and H plus, that's our oxidizing agent. Then we have to look, if we go backwards, what's the oxidizer, what's the reducer going backwards? So if I reverse this first equation, the top one, what's happening to copper 2? Well, if I go backwards here, copper 2 is gaining electrons to go to copper metal. And so if something gains electrons or takes electrons, we call them an oxidizer. Or we could use the conjugate relationship. The conjugate relationship is if one side's the reducer, the other side's the oxidizer. And if one side's the oxidizer, that must mean the other side must be the reducer. And so over here, the conjugate relationship tells me NO and H2O, that's my reducer. And so this is the oxidizer, and this will be the reducer. And then I look, am I going uphill or downhill? So I either compare the reducers or compare the oxidizers. We'll compare the oxidizers since it occurs on the left side. So which one's a stronger oxidizer, nitrate and H plus or copper 2? I go over here and look, I have nitrate and H plus here, and then down here I have copper 2. So which of these are stronger? Nitrate's stronger. And so this is stronger to weaker. That means this is going downhill. Stronger means more reactive, less stable. Weaker means less reactive, more stable. And that means if this holds, because of the conjugate relationship, the reducing agents must do the same. And so if I take a look at the reducing agent, here's copper here. Here's NO and H2O. Copper is a more powerful reducing agent than NO and H2O, which is a weaker reducing agent. And so this is a stronger reducing agent. This is weaker. So this is going downhill. This is driving force. We're going from stronger to weaker. Stronger is higher in energy, more reactive. To weaker, which is lower in energy, less reactive. We call this a driving force. So copper, if we use single replacement, does not react with nitric acid. But if we use the chart method, copper reacts with nitric acid. And let's take a look at the reaction between copper and nitric acid. Hopefully there's no ad. The reaction of copper with nitric acid. I don't know what happened to the audio. Okay, so it's pouring the copper into the flask. Actions are. Do you see the reaction? You can see the bubbling of the gas there. The gas that's being produced is NO gas. NO gas is nitric oxide. NO gas is not brown. The brown gas comes from additional reaction on top of it. And so this is what we call a colorless gas. Colorless. And so initially we generate this colorless gas. But the NO gas reacts with O2 and air. And when that happens, we'll form NO2 gas. So we'll need two NOs to react with an O2 to form two NO2s. This is the brown gas here that we see in this reaction. Let's see if we can go back without the caption. So this is the nitric acid down here. That's a copper metal, and immediately you can see the color change. There's a blue-green color. The blue-green color is from these ions. These are blue-green, depending on how concentrated they are. And so this is aqueous, actually. So it's giving the color. And then the gas is being generated, and then the NO2 gas is poisonous, so what they're doing is they're bubbling it through water to kill it. Try to kill the gas before they let it. They don't want to breathe this stuff here. But you want to do this in the hood. It's quite dangerous. Here you can see blue now from that. All right, any questions on this?
What is the final reaction then between copper and
This is the final reaction here. This is kind of funny the way it's written. This is what we call net ionic equation. Net ionic equation just shows us the species that are reacting. And so if I have 4 H pluses, I need 4 nitrates, but not all the nitrates. Or if I have 8 H pluses, I need 8 nitrates, but not all the nitrates are reacting. So we're just looking at for the nitrates that aren't reacting, because nitric acid would be 8 H pluses and 8 nitrates. That means 6 of the nitrates aren't reacting. Those 6 nitrates that don't react, we will ignore them. And so this is just the net reaction, looking at the species that's reacting. So this is the overall reaction. But what we say in words is this: copper metal is oxidized by nitric acid to form copper 2 solution, which is blue-green or blue, and NO gas. The NO gas subsequently reacted with air to form nitrogen dioxide, NO2, which is the brown gas. That's what's happening in this particular reaction. But the point of this is that the single replacement predicted no reaction between copper and nitric acid, but that's wrong. There is vigorous reaction between copper and nitric acid. And so single replacement, you have 2 choices. One, memorize all the exceptions, and there are a lot of exceptions to single replacement, and then memorize new patterns. You want to memorize new patterns? I told you to memorize the chlorine pattern. No, you don't. You don't want it. You want a more general method. And so even though this seems to be more work, and it's not in the book, it's less memorization. Less memorization, because you don't have to memorize the exceptions. Now, the other alternative is you never give the exceptions. If in the homework there were no exceptions, then we just ignore all the exceptions and say, okay, hopefully you don't run into exceptions. But unfortunately, and I was going to do that, I was going to skip all this. But in the homework they threw in the chlorine, so then they have the nitric acid. So then I thought I'd better talk about this, because this is an easier way than memorizing that copper and nitric acid do react to form this. There's one more common exception, which we'll look at after. Let's take a break now, and then we'll look at the common exception next. Normally, the way we do it is, let me show you here. Sodium metal, what was the formula you got for sodium metal? Na. Solid, liquid, gas? Solid. Charge? No charge. Potassium iodide? Ki. Now, Ki, normally this is gonna be mixed with potassium iodide AQ. Here it's a little bit ambiguous because potassium iodide you buy as salt tablets or they dissolve in water. And so here it could either be Ki solid or KiAQ. In this case, we're gonna say KiAQ. And so normally what I'll say is to make sure it's not ambiguous, I'll either say Ki aqueous or aqueous Ki. And then we know that it's gonna be aqueous. And then what did you form? Sodium iodide and potassium. Now sodium iodide, all sodium and potassium salts are soluble, so this is gonna be aqueous, but potassium is a ion or metal? Yeah, it's the element. The element potassium is a metal, solid, like this. And then this is balanced. Then we look at the activity series. We compare the two elements. Sodium is an element, potassium is an element, and which one's more active? So we go to the activity series and we take a look. It goes lithium, potassium. Potassium is more active than sodium. And so we say this is more active. This is less active. And so is this uphill or downhill? This is uphill. This is uphill. And therefore, you know, we say, instead we say this. We say NR. NR just stands for no reaction. But what we should say is there's no single replacement reaction, because there is a reaction here. Can you figure out what the reaction is? You can figure out the reaction, what the reaction is if you use the chart method. And so try to repeat this reaction, but use the chart method instead to see what the reaction is. Not have finished it, but let me talk about some very common mistakes. Number one, sodium. So many people write sodium Na+, but is that sodium or is that sodium ion? That's sodium ion. And did I ask for sodium ion or did I ask for sodium? Yeah, I asked for sodium metal. To emphasize it, I wrote sodium metal, not sodium ion. So this is. Does that make sense? This is totally wrong. It's not Na+. It's going to be Na. Okay, the next thing is, okay, when people were doing the inventory, people wrote this for potassium and this for iodine. That's totally wrong too, because yes, this is potassium, but that would be potassium metal or elemental, but this is potassium iodide. Potassium iodide is an ionic compound. Ionic compounds are going to consist of what ions? So if this is Ki, it's going to consist of K plus and I minus. It makes a huge difference. You know, it's going to make a huge difference in the reactivity. You know, sodium ions that you eat, people like the taste of sodium ions. They put it on their food. Chloride doesn't have any flavor. And so when you put it, in fact, I saw a very interesting article. I'll share it with you here. You know, sodium is, people who have high blood pressure, they want to cut down their sodium intake, right? And, but a lot of people like salty foods. Some people just get used to it. I just got used to low salt. But other people want some kick to their food, so they want to put salt. So Frito-Lay has this patent. What was it? The article was called "Making Salt Taste Saltier." Have you ever heard that? How can you make salt taste saltier? Hopefully this comes up. What's going on with CME news search? For some reason that didn't work. I guess I got logged out. That's probably what happened. You can join these professional societies as a student, and the student membership price is very cheap. I'll have to show you the article later. So when people are saying we need to lower the sodium in our diet, are they talking about sodium ion or are they talking about sodium metal? In other words, do you eat sodium metal? So if you want to put some salt on your French fries, you wouldn't put sodium metal on the French fries. You put sodium ion on. If you put sodium metal, your tongue might catch on fire. Want that to happen. The same thing over here. You know, potassium metal and potassium ion are totally different. He calls this Dr. Jekyll and Mr. Hyde, and that's the behavior, the chemical properties. So it's potassium ions and iodide ions. And then there's one more thing in the inventory. Do you know what one more thing is? It's water. And so I saw some of you got it. Okay. What did you do next?
Figure out which is like the reducer and which is oxygen.
Yeah, so which is the reducer? And then sodium?
Reducer.
Reducer. Potassium ions.
Oxygen.
Iodide?
Reduces.
Water?
Either.
Yeah. And so here, sodium is a very powerful reducer, but sodium ions would be a very weak oxidizer. And so we don't worry about sodium chloride oxidizing anything here, because sodium ions are so weak. Anyway, this is potassium ions, are oxidizers, but they're extremely weak too. Potassium ions were near the bottom of this chart, although I don't know why I didn't have potassiums. None of these are perfect, unfortunately, here. The potassium ions are here between lithium and sodium ions, so they're pretty weak. Lithium ions would be the weakest oxidizer, weakest oxidizing agent away. Iodide? Iodides are decent reducing agents, but you know, compared to sodium metal, iodide is a lot weaker. And then water. So anyway, we picked the strongest reducing agent. We have three: sodium, iodide, or water. Which one's the strongest reducing agent? Sodium, well the strongest is lithium. And then sodium is here. And then iodide is here. And then water is here. So which one's strongest? Sodium. And so what does sodium do? Well, sodium's a reactant. This sodium's a product, so we have to flip this equation over to make sodium a reactant. And so I can't copy that equation as is. I take sodium solid, and that's going to go to sodium ion plus an electron. So what sodium can do is it can lose an electron to form sodium ion. Okay, that's the strongest reducing agent, so this is what we expect to happen. Sodium's gonna be losing the electron. Sodium loses electron easier than iodide. It's a bit harder to take the electrons from iodide here to form ID. And it's quite a bit harder to take the electrons from water. When water loses electrons, it forms oxygen gas here. And it's pretty hard to oxidize water. All right. Then we look at the oxidizing agents. We have two oxidizing agents, potassium ions and water. Yeah. Potassium ions are down here, water's here. So water's a better oxidizer. And so what we're going to do is we're just going to copy the equation down here. Water's a reactant. And so I need two waters here plus 2 electrons is going to yield hydrogen gas and 2 hydroxides. So hydrogen gas plus 2 hydroxides. Okay, and then what was the issue with this?
The electrons aren't.
Yeah, this one is, the electrons don't balance. You see, this one has 2 electrons on the left, but we only have 1 electron on the right. How can we fix this?
Multiply the top by 2.
Yeah, multiply the top by 2. So we'll do that. 2, 2, 2. Okay, now we have 2 electrons and 2 electrons. And when we have things that appear on both the left and the right, we can cancel like that. And so overall, I'm going to have 2 sodium solids plus 2 H2O liquids. This is going to produce 2 sodium ions plus hydrogen gas plus 2 hydroxide ions. Sodium ions and hydroxide ions will form sodium hydroxide, and so we end up with sodium hydroxide and hydrogen gas. These are the aqueous here. Now we need to know if there's a driving force. So what we do is we'll label these. If this is a reducing agent, then its conjugate is a, and if this is a oxidizing agent, then its conjugate is, yeah, good. So what we'll do is we'll just label this reducing agent, oxidizing agent, and then these two form our reducing agent here. And then we compare whichever side's easier. So if we compare the oxidizing agents, water versus sodium, so water's here, sodium ions here. Water is closer to fluorine, so water's stronger than sodium ions, which would be weaker. And if this is true, then it must be correct that sodium must be a stronger reducer than hydrogen. So let's take a look at sodium is right here next to lithium, and then hydrogen's up here, so it is stronger. So this is stronger, this is weaker. So if we're going from stronger to weaker, that's driving force. It's downhill. And so the question is, what happened to the potassium iodide? Actually, nothing happened to the potassium iodide. The potassium iodide's still there. It just didn't react. And so this is what we call a net ionic equation. It doesn't show everything, it just shows what reacts. And so if you took, this is what happened at UCSB. You know, UCSB is right on the ocean. So people used to like to do this. They like to take sodium metal that they had extra and dispose of it into the ocean. Probably not good, but they did. They threw it in the ocean, but the ocean's full of salts. What happened to all those salts? Nothing happened to all those salts because the sodium reacts with the water. It doesn't react with any of the salts. And so the salts are what we call spectators. They just don't do anything. All right, so what we had here are 3 major exceptions to single replacement. Let me summarize the exceptions. The nice thing about single replacement is it's very quick and easy. And so there's an advantage to using single replacement. The disadvantage is it doesn't always work. And there are three major times it doesn't work. One is when we use a oxidizing acid. Versus mineral acid. So an oxidizing acid would be like this, HNO3. A mineral acid would be like this, HCl. The difference between an oxidizing acid and mineral acid is this. In a mineral acid, H plus is the oxidizer. Is chloride a very good oxidizer? So when I look at chloride, chloride is not an oxidizer. Chloride is a reducer, and it's a very weak reducer. Chloride's very stable. And so when I think about a mineral acid, the anion like this is what we call, let's say, a spectator. You know, nothing's going to happen there, typically. However, when I look at an oxidizing acid, I still have H plus. H plus is an oxidizing agent. It's on the left side of that chart. But nitrate is also a oxidizing agent. Chloride is a weak reducing agent. Which oxidizing agent is stronger, H plus or nitrate? So when I look at the chart here, here's H plus, which is for acids. And here's nitrate. Actually, where is nitrate? So none of these charts are perfect, unfortunately. So let me go back. Actually, there is one chart that's quite good. But that chart is in the Chem 1A book. Nitrate is very common. So typically it's found in these charts. I don't know why it's not found here. Let me try it. Our chart. Here. It's up here. H plus is here, nitrate's up here. So what that tells you is this is a stronger. With H plus. This is a weaker. And so some people call this the synergistic effect. You know, nitrate with H plus is stronger than H plus alone. But it's nitrate that's really doing the reaction here. And so in an oxidizing acid, the anion, the X, you know, this is the HX part. The X is more reactive than the H. In a mineral acid, the X is not. It's the H that's reactive. Does that make sense? So an oxidizing acid, the anion is a more powerful oxidizer than the acid itself. Okay, so whenever you're dealing with an oxidizing acid, now what are the oxidizing acids? How about HI? Is HI an oxidizing acid? No. HBr, oxidizing acid? No. What about HClO4? Is that an oxidizing acid? What do you think? HClO4. Well, let's try this. Let's do HClO4 versus HI. HClO4 consists of H plus and ClO4 minus. HI consists of H plus and I minus. Both of these have H plus, and H plus is an oxidizer, so they should be equal in oxidizing strength, right? However, now ClO4 is not on our chart, is it? ClO4 isn't on our chart, but what makes nitrate a strong oxidizer? Do you know what makes nitrate a strong oxidizer? Well, the oxygen plays a role in it, but what's the
electron.
it's because of nitrogen. It's because of what, it's because oxygen takes electrons from nitrogen, and nitrogen's left with how many? +5. And so it's because of nitrogen's +5, which makes it very electron poor. Oxygen's happy at -2 each, right? And so there's no problem with oxygen. Well, what is the chlorine's oxidation state over here? +7. Do you see that this is going to be a very powerful oxidizer? In fact, it's so powerful it caused the Pepcon disaster in Nevada, right? The Pepcon explosion. And so this is perchlorate. And so this is a powerful oxidizer. Stronger oxidizer than H+. Does that make sense? Whereas when I look at iodide, is iodide really electron poor? Is iodide going to oxidize anything? No, iodide's electron rich. And so this is what we call mineral acid. This is what we call an oxidizing acid because of the perchlorate. The perchlorate is very electron poor because of its high positive charge on chlorine. Chlorine doesn't want a positive charge. Chlorine wants a negative charge. And so that's the exception. If we have an oxidizing acid, watch out. So if you have perchlorate or perchloric acid, no, you wouldn't use single replacement. If you have HI, then go ahead and use single replacement. If you have HCl, use single replacement, no problem. HBr, use single replacement. But when you have something like this, then no, don't use single replacement. Or if you don't like memorizing that, then just don't use single replacement at all. Just use the chart method, if you don't want to memorize this. The next exception is this. So this is one. What was the next? The next exception is when we have everything misassigned. And so let's say we had something like fluorine plus potassium iodide. And so in the single replacement, we're going to say potassium's the oxidizer, but that means fluorine has to, if potassium is the oxidizer, who loses? Well, that means fluorine must lose, right? Does that make any sense to you? No, this is totally wrong. And so single replacement fails for this. And so it's a case where, the element is a more powerful oxidizer than the cation here. And so A is a stronger oxidizer than, what is this, A plus BX? A is a stronger oxidizer than B plus X. Here, X is a stronger oxidizer than B plus X. So here, X is a stronger oxidizer than B plus X. A is a stronger oxidizer than B plus X. Therefore, it's going to fail because single replacement calls B plus X the oxidizer. The third exception is when water is a stronger oxidizer or a stronger reducer than what's given. Than what is given. So, in order to prevent people from making a mistake here, Normally what's given is this. Example is what we just did, sodium, or what did we do, potassium? Sodium plus potassium iodide. To avoid this problem, what we do is we change this to sodium plus H2O. If I would have done sodium plus H2O, then you would have done it like this. In single replacement, this works. This is okay for single replacement. This has to be AQ. The way we make it okay for single replacement is we write it like this, A plus Bx. A plus Bx here is going to go to sodium hydroxide plus hydrogen. Yeah. And so if we wrote the single replacement like this, it would have worked. But here there was no reaction. Mm-hmm.
So if we wrote Ki as a solid, like there's no water present for whatever reason, then there wouldn't be a reaction.
There wouldn't be any reaction, right? If Ki, that's simple. If Ki was a solid, no reaction. There's no water present, so nothing would have happened. So that's good.
Would we still use the chart method then if Ki was a solid?
If Ki was solid, you would use the chart method. You could use the chart method to see, or you could use single replacement, you know, to see. All right. So, any questions on this? The chart method. Is the chart method? What do you think of the level of difficulty of the chart method? Easy. Okay.
Just like slightly confusing.
Slightly confusing. It just takes some time. If you do some practice problems, you'll get it. Now, Chapter 9 is a continuation. Chapter 9 just continues chemical reactions, but we're going to throw in one other thing to this. We talked about the solubility rules. Okay, next what we're going to do is we're going to talk about electrolytes. And so that's in 9.1. And then we'll look at net ion equations. So let's try this out here. This is reactions part 2. We'll talk about electrolytes. We have strong, weak, and non-electrolytes. Strong electrolytes dissociate into ions in solution. So if I have table salt, sodium chloride solid, it's water soluble, because all sodium salts are soluble. So that gives sodium chloride aqueous. But sodium chloride aqueous is a strong electrolyte. And so what that means is that the sodiums break apart from the chlorides. And so this is going to form sodium ions, aqueous, and chloride ions, aqueous. And those ions are going to be moving independently of one another. Show that here. This dissolving sodium chloride is called dissolution. So let's say I have a salt crystal here. The water has come along and tug on the ions. And they tear apart the salt crystal, one ion by one ion. So water is a plucking of them. And then what we end up with is we have ions floating around in water independently of one another. And so that's what this means. So these are what we call this is the chloride ion, that's a sodium ion here. We call these hydrated ions or solvated ions. So we have these aqueous ions, and that's what we're showing in that video here, the aqueous ions. Okay. All strong electrolytes do this. What are strong electrolytes? Strong electrolytes are the soluble salts. Strong acids. And strong bases. So what is a strong acid? A strong acid, all acids begin with H, and there's 7 common strong acids that we tend to try to memorize. 7 common. Do you know the 7 common strong acids? The 7 common strong acids are HClO4, which we call perchloric acid, HClO3, which is called, if this is perchloric acid, that is chloric acid. HI, what do you call that? Hydroiodic. HBr, HCl, hydrochloric. How many do I have? 1, 2, 3, 4, 5. HNO3, nitric acid, that's 6. So I'm missing 1, 7. H2SO4, right? What's H2SO4 called? Sulfuric acid. So these are the 7 common strong acids. People memorize the 7 common strong acids. If you memorize the 7 common strong acids, then you can assume the other acids are weak. So whatever else begins with an H is going to be weak. Like phosphoric acid, weak. It's not terribly weak. Nitrous acid, weak. Hydrofluoric acid, weak. Carbonic acid, weak. So all the others are weak. That's not always the case because have you heard of what is it, hydroantimonic acid or something like that? You know, the strongest acid? The strongest acid known is about 10 to the 19 times stronger than H2SO4. Can you believe that? Something that much stronger? 10 to the 19, it's hard to comprehend. So what that means is this. HCl is normally a gas. And so in gas form, we can call it hydrogen chloride gas, or we can call it gaseous hydrochloric acid or something. And typically people call this hydrogen chloride gas. And then they dissolve it in water. When they dissolve it in water, we'll form HCl aqueous. HCl aqueous we call hydrochloric acid. But HCl is a strong electrolyte. So this is a strong electrolyte. What happens is it splits up in water. And what's it going to split up into? It's going to split up into H plus and Cl minus. That's it.
And then both products would be aqueous.
Yes, both products would be aqueous here. And so the same kind of thing happens. The hydrogens break free from the chlorides and then they're floating around independently in the water. The strong bases, I'm not going to talk about those yet. But normally, actually, maybe I'll talk about these. These are the soluble hydroxides. Etc. Actually, that's all I'll talk about as far as bases go. Bases are a bit more tricky. Okay, 2, we have the weak electrolytes. The weak electrolytes, what we say for weak electrolytes is they partially dissociate. Into ions in solution. And so an example of this would be acetic acid. Acetic acid is HC2H3O2. So if we have acetic acid, which is going to be aqueous, what we see is that it partially dissociates. So what we do is we write these two arrows like this, and we partially dissociate this into H plus and acetate, C2H3O2 minus. And so something like acetic acid remains mostly as acetic acid molecules. And then just a few of these molecules will break up into ions. So over here it's like 99% molecules, and then actually it's less than 1% ions here. 99 point. It's more like 99.9% molecules. So we can look at the dissociation of acetic acid here. Okay. Doesn't really show it so well. So let me try to draw it out. If you have a beaker that's labeled HCl, like this, so you have a beaker of hydrochloric acid, what are you going to find? You're just going to find H plus and Cl minus. That's it. However, if you have a beaker that's labeled acetic acid, it's a bit different. If it's labeled acetic acid aqueous, then what are we going to find? We're mostly going to find acetic acid molecules. And so the molecules stay together as HC2H3O2 molecules. And maybe 1 out of 100, or less than 1 out of 100 molecules will break apart. And they'll break apart into the ions H plus and C2H3O2 minus. So, therefore, we call this a strong acid. HCl is a strong acid because a strong acids give lots of H plus. Whereas acetic acid we call a weak acid. It's a weak acid because we don't have as much free H plus available to react. It's the H plus that's reacting. So, weak acid, little H plus. The molecules stay together. The last type of electrolyte is called non-electrolyte. Non-electrolytes don't break apart. So non-electrolyte would be something like this. Sugar. So if I had something like glucose, and it's a solid, glucose turns out to be soluble in water. So when glucose dissolves in water, I'll form glucose aqueous. But it doesn't break apart. This is non-electrolyte, so this does not dissociate. So non-electrolytes do not dissociate. It's the same thing with something like if I have this. This is ethanol. Ethanol is liquid, and if I dissolve this in water, I'll form aqueous ethanol. But this does not dissociate also. It just stays as ethanol molecules. Speaking of ethanol molecules, you know there's a company that's selling deuterated ethanol? Have you heard of that? Drinking Science. Let's see if this comes up. So this is normal ethanol. The hydrogen can be whatever isotope you want. But deuterated ethanol, they change the hydrogen on the alcohol D here to D, to deuterium rather than hydrogen. So this is the thinking for deuterated alcohol. Of course, it's going to be very expensive because deuterium is not so cheap. But Drinking Science, deuterated ethanol and biochemical booze mimics, putting the D in drinking. Ethanol gets the blame for hangovers. And so the whole idea behind this is to minimize hangovers and yet still have the other effects of alcohol. And so the reason they're using deuterium here is, one of the reasons they're thinking you get hangovers is because it's rapidly, alcohol is rapidly converted to acetaldehyde. Have you heard of acetaldehyde? Acetaldehyde is a class of compounds called an aldehyde. And probably the most common aldehyde is formaldehyde. Have you heard of formaldehyde? And so this gets converted, ethanol gets converted into like formaldehyde-like chemicals. Formaldehyde good? No, formaldehyde is not so good, and so that's what leads to the hangover.
Speaking of hangovers, I know there's people who would do the IV drips.
Oh, yeah,
Hire
the IV drips is
yeah,
good,
companies.
for sure. And they have all these other things that they use to
That's a solution of saline.
yeah, to change this. That's probably to help with the dehydration that you might experience with this. The whole concept here is, you know, this conversion to formaldehyde with deuterium slows down. So if it slows down, then you aren't going to get as big of a hangover. It'll be just distributed. And so you can pay extra to get some deuterated alcohol. I think you can buy it now if you want. Yeah, and there's a company. This company is well, I don't know if this company's started yet, but he said the first glass cost $5,000 to make it. But it's gonna get, of course, it's gonna get much cheaper, you know, with volume. Where is it? Here it is, deuteria. Here it is. The first screwdriver costs around $5,000. Is it worth it? I don't know. Okay, well, anyway, alcohol would be a non-electrolyte. So the way we do this is we memorize. Strong electrolytes are the strong acids, strong bases, soluble salts. Weak electrolytes are the weak acids, weak bases, and heavy metal salts, some heavy metal salts. So weak electrolytes partially dissociate. These are the weak acids, weak bases, and some salts, and some heavy metal salts. Heavy metal would be like lead. These metals lower down in the periodic table. You know, lead's pretty low. Thallium, mercury, gold even. And non-electrolytes would be everything else. Everything else would be, if it's not strong and it's not weak, then we're just going to assume it's non. So this is how we determine. So, let's take a look at some examples here. This is ethanol. So ethanol, that is a non-electrolyte, so it doesn't dissociate. So here's an ethanol molecule, it's water. And all the ethanol molecules are all intact and broken apart. Over here is copper 2 chloride. Copper 2 chloride is, actually we're out of time, is a soluble salt. So soluble salts break apart. So this is going to break apart into 1 copper and 2 chlorides. Or no, this is copper, yeah, this is copper 2 chloride. 1 copper and 2 chlorides, all of them. And then finally we have a weak one here. This weak one is acetic acid. So like 99 out of 100 will just be the molecules, and then 1 out of 100 will dissociate into ion. And we could test this using light bulb here. I'll talk about that next time. We're out of time here. In fact, I'm going to talk about this tomorrow because this is what we're doing in lab tomorrow. We're looking at, well, it's a demo lab, so I'm going to do the lab. You're going to just watch.
So this has to do with electroconductivity, right?
Yes.